Hello and welcome to the 21st session of the Introductory Biostatistics Distance Learning course. Today we're going to talk about linear regression and correlation. Okay, so let's talk a little bit more about what exactly we're going to be talking about. So correlation is something we use when we have a continuous outcome. Remember, we always want to think about the type of data that we're working with, a continuous outcome, as well as a continuous covariate. Okay, and then within correlation, we have two different types. One is the Pearson correlation, and this is a parametric procedure. So remember, that makes normality assumptions. And then we have a corresponding non-parametric measure, which is called the Spearman. And that's non-parametric. Okay, and then after that we'll talk about linear regression. And again, that's continuous outcome but the covariate can be continuous, it can be binary, it can be categorical. So it accommodates many different types of covariates. That's one really nice thing about linear regression, and probably why it's the most widely used statistical procedure. Then we'll talk about how to interpret coefficients that come from a linear regression. So that's going to be the key message for us, is the interpretation of the coefficients. And then we'll talk about the connection between regression and correlation. So there's a lot here. It'll probably take us 2 sessions to get through all of it. Okay, so let's take a look at this progression that we've been making with regard to where we are in terms of our development of the course. Okay, so you remember, we always want to think in terms of the type of data that we're dealing with, in terms of the outcome variable, the explanatory variable or covariates. And so remember, we talked about having a continuous outcome and a binary or dichotomous explanatory variable. We used the t-test, which was the parametric test, or the corresponding non-parametric test called the Wilcoxon test. Then, when we had a continuous outcome and a categorical explanatory variable, we used ANOVA. But it turns out ANOVA is just a special case of linear regression. So linear regression can go there as well. And incidentally, the t-test is just a special case of linear regression. So we could put linear regression here as well. But here we're focusing on the case where we have a continuous outcome as well as a continuous covariate. We can use correlation, which we'll talk about, or linear regression as well. And then we've also talked about in the last sessions about when we have a dichotomous outcome or binary outcome, as well as a binary or dichotomous covariate, we can use the chi-square test, and later in the course we'll talk about logistic regression. Okay? Alright, so always think in terms of the types of data that you're working with, particularly the type of outcome variable you have, and the type of explanatory variable or covariates that you have. Okay? Because once you have established the types of variables that you're working with, the type of statistical analysis that you need to do should pretty quickly fall out. Okay, so taking a look at the big picture, so far we've discussed tests where we compare 2 or more groups to each other in terms of some outcome of interest. Okay, so in these cases we wanted to determine if there was an association between being in a particular group. Remember, there was, for example, the different types of of multiple sclerosis. There was the secondary progressive and the primary progressive and so on. So we were looking at group membership and how that affected an outcome of interest. Okay, but now we're interested in seeing if there's an association between two continuous variables. So both a continuous outcome and a continuous explanatory variable. Okay, so for example, is a person's weight associated with his or her height? Okay, so two continuous variables. That's where we are now. Okay, so as an example, let's there's this thing called BPF, which is the most common measure of brain volume. Okay, so BPF is this measure of brain volume. Okay, and it's likely that BPF goes down with age. Okay, so as your age goes up, BPF goes down. Okay, that's among adults, obviously. Okay, so the best way we can assess this is to look at a graphical display of some data that people have collected in a scatter plot. We want to assess whether there's a relationship between age and BPF. So here's that aforementioned scatter plot. Here's age on the horizontal axis and BPF on the vertical axis. And if you were to draw a line, a best fitting line here, you would say it looks something like this, right? So as age is going up, here are the 20-year-olds, 30-year-olds, 40-year-olds. So age goes up as you go right. It appears that BPF is going down. Okay? All right. So that's just an informal assessment we did just by looking at the plot, but obviously we want to do more formal statistical tests to determine if there's a relationship. Okay? So let's now talk about correlation. Okay, so what is the definition of correlation? Okay, it's the degree to which two continuous variables are linearly, so linearly means a line, linearly related. Okay, so this is a very important point, that it's linear. Okay, two continuous variables might have a curvilinear relationship, such as this. There's clearly a relationship between whatever x variable and y variable, but it's not a linear relationship. I can't represent it with a line. Okay, so that's a key point to keep in mind. Correlation is the degree to which two continuous variables are linearly related. Okay, so correlation, which we often define with the Greek letter rho. It looks like a P, but it's the letter rho. It ranges from, if I just put it here in the middle, it ranges from -1 to 1. Okay? So a -1 means perfect negative correlation. That means for every unit that x increases, y decreases by that unit. And 1 is perfect positive correlation. That means for every unit x increases, y also increases by 1 unit. Okay? And a correlation of 0 means that there's no linear relationship. So if rho equals 0, that implies that there's no linear relationship. Okay? All right, so let's take a look at some examples of these different types of correlation, or different strengths of correlation. Okay, so the first example is going to be perfect positive correlation. Or this isn't perfect, sorry, it's positive correlation. If it were perfect, everything would fall directly on a line. You can see it's pretty close to a line, but it's not perfect. So this is positive correlation. It's not, rho wouldn't be quite equal to 1, but it would be very close. Okay? Then the next example is an example of negative correlation, just as you might have expected. So as one variable increases, the other variable decreases. Okay? So that's negative correlation. Okay? Then when we talk about no correlation, it can take one of several different forms. Okay? So here's an example of no correlation. It doesn't really look like there's much of a relationship between x and y. Okay? So something like that. Okay? So this is one way in which we could have no correlation. But again, you'll remember that we said that correlation measures the strength of a linear relationship. So we could have two variables that have a very strong relationship with each other, but have no correlation or no linear relationship. So here's an example. Clearly there's a strong relationship between these two variables. In fact, it's quadratic, but there's no correlation because we cannot represent the relationship between the two with a line. Okay? So just because there's no correlation doesn't mean that there's no relationship between two variables. It just says that there's no linear relationship. Okay, so what does the mathematical definition of correlation look like? So again, just as we always say when we see formulas, don't worry about the particulars of the formula, but instead think, how can this formula provide me with some insight? Okay, so this is saying that the correlation between x and y is equal to the covariance between x and y divided by the variance of the square root of the variance of x, which is the same thing as the standard deviation of x, times the standard deviation of y. Okay? So this equation says that if the covariance between two variables is the same as the variance in the two variables, then we have perfect correlation, okay? Which is another way of saying that all of the variability in x and y is explained by how the two variables change together, okay? So that's just the definition of correlation, okay? And so how do we estimate this? This is the definition, but how do we estimate it once we have some data? Well, we can use this thing called Pearson's correlation coefficient. And what does that look like? Let me pull that up. Okay, here's the equation. Okay, so again, don't get too confused, but this is just the variance of x, and here's the variance of y. And again, it becomes the standard deviation because we're taking the square root here. Okay, and the covariance is just how they vary together. Okay, so we take an observation minus its mean times the corresponding y observation minus its mean. Okay, so that's how we get this value called R, which is Pearson's correlation coefficient. Okay, and remember at the beginning we said that Pearson's correlation coefficient is a parametric test. Parametric. Okay, and what does that mean? It means that in order for this estimate to be valid, we require that both x and y are normally distributed. Okay, and this is something that can be sensitive to outliers. Okay, so this is a parametric. Pearson's correlation coefficient is parametric version of the correlation, and it requires that both x and y are normally distributed. Okay, so let's take a look at this example a bit about age and BPF. So the whole data set is rather large, but let's just take a look at a small portion of it. So here's some people and their ages and their BPFs. Okay. So each patient has both their age measured and their BPF measured. Okay? And so our hypothesis was that as age goes up, BPF goes down. Okay? As age goes up, BPF goes down. Okay? And so if we were to calculate the sample Pearson's correlation coefficient for the full data set here, we would get R equals negative 0.577. And the negative tells you that it has this sort of relationship. As one goes down, as one goes up rather, the other goes down, just as we suspected. Okay? But hopefully you're getting really used to how statistics proceeds. Just saying that this is the correlation is not enough. We need to formally test if the correlation coefficient is significantly different from 0. Because what if we were to construct a 95% confidence interval for this estimate here, and if the 95% confidence interval, which goes between A and B, if 0 falls in between here, then we know that it's not significantly different. Okay? So we want to do a formal hypothesis test to see if the correlation coefficient is significantly different from 0. Okay? And if it is significantly different from 0, then we can conclude that there is in fact an association between the two variables. Okay? So, what do we need in order hypothesis test. What do we need in order to be able to conduct this hypothesis test? Well, we need our null hypothesis, which is that rho, the population correlation coefficient, is equal to 0. Okay, so that's our null. But to carry out the test, we need an estimate of the standard error. So hopefully you're getting really used to this setup. We can't just have an estimate. We need an estimate of its standard error to see if it's significantly different from 0. So we need a standard error of R. And then we need to know the distribution of our test statistic. Remember, we compare it back to the distribution, and then that gives us our p-value. Okay? So we need 1, the estimate of the standard error, and 2, the distribution of the test statistic. Okay? Okay, so what does the standard error look like? We're not going to go through the derivation of the standard error. We'll leave that to the statisticians. We're just going to take it as given. Okay, so let me just quickly show you what that looks like. Here's the standard error of R. It's the square root of 1 minus R squared divided by n minus 2, where n is the number of patients. In our sample. Okay, so you can see the standard error goes down as we get larger sample sizes, right? That makes a lot of sense. As we get more and more people, if we get a larger n, we're dividing by a larger number, which gives us a smaller standard error. Okay, so we're more sure about our estimate if we have more people. Okay. So that's our standard error, and then we said we also need a distribution. Again, we'll leave that to the statisticians, but it turns out that if we were to construct this here, the resulting distribution of the test statistic is a t-distribution with n minus 2 degrees of freedom, where again n is the number of patients. And you can see we take our estimate, subtract off the hypothesized value. Remember, our null was that rho equals 0, so 0 is our hypothesized value. That's why we're subtracting 0. Divide by the standard error, that was this piece, and then we can just simplify that with some algebra and we get this. Okay, so that's our test statistic. So now that we have our test statistic, we can go through our 7 steps of hypothesis testing as we normally do. So Step 1, state the null. Here it's that correlation is equal to 0. Obviously, the alternative hypothesis is that the correlation is not equal to 0. Our data, we have two continuous variables, both a continuous outcome and a continuous covariate. The test we're going to conduct here in this particular example is the Pearson correlation coefficient. Okay, so these are the 3 steps we can do without Stata, and then starting with Stata, we say once we plug our data in and conduct the tests, we get our test statistic. Remember, we said it was a t distribution here, so here in this BPF example we've been working with, in this BPF example that we've been working with, it turns out that t is equal to negative 3.67. Once we have our test statistic, we can get the corresponding p-value, which in this case is equal to 0.001. Then we compare that p-value to 0.05. It turns out this 0.001 is less than 0.05, so we reject the null. Okay, and then finally in step 7, we conclude that there is a significant association between BPF and age. And I don't want to stop there because that doesn't tell me much, but I would say something like, as age goes up, it appears that BPF goes down, okay? And the reason I knew that was because my estimated correlation coefficient was negative, and that also comes through in the test statistic, okay? It's negative. So as one goes up, the other goes down. Okay, so what does this look like in Stata? Let's pull up some output. Okay. So pwcore is the command in Stata. Age and BPF are the 2 variables that we're looking at. This just tells us to tell us whether it's significant or not, and then this tells us to tell Stata to display the number of observations. So obviously age has a perfect positive correlation. It's kind of funny that they display that. A variable with itself will always have a perfect positive correlation, but instead we're interested in this one here, which is the negative correlation between BPF and age. Then the p-value is here, 0.001. Okay, and so that's why we were able to conclude based on the p-value, and because the estimated correlation coefficient is negative, that's why we were able to conclude that as age goes up, BPF goes down, and it is a statistically significant association. Okay. All right. So, just like before, when we have a parametric test, it has those assumptions, right? Here, our assumptions were that both age and BPF are normally distributed. Okay, so that's why it's a parametric test. It has this parametric assumption, which may not hold, this might not be the case. Okay, so just like we always had before, we have non-parametric alternatives. Okay, so we have nonparametric correlation. Okay, so if the assumption of normality for each of the variables does not hold because of outliers, or maybe because we have ordinal data, we have this nonparametric correlation, which is called the Spearman correlation. Okay, so as before, so you might be thinking, well, if the nonparametric holds in all cases, it makes fewer assumptions, why wouldn't we just always use the nonparametric? And the reason, just as it was before, is because nonparametric tests have less power if the assumptions hold. So if those two variables, age and BPF, are in fact normally distributed, we would lose some power by looking at the nonparametric correlation. What do we mean by losing power? It means we're less able to detect a difference, which translates into the nonparametric correlation will have a higher p-value if the normality assumptions hold, okay? So that's always the case, okay? So nonparametric tests are good because they have fewer assumptions, but the cost is that we lose some power, okay? In other words, the nonparametric tests give us higher p-values when the assumptions are actually met, okay? Okay, so as with, when we looked at the Wilcoxon test, which was a very famous nonparametric test, Spearman's correlation coefficient, so let me just, Spearman's correlation coefficient is based on ranks. Remember, we looked at the ranks when we were talking about the Wilcoxon test, and similarly here we're looking at ranks. Okay, so what does the equation look like? Here it is. Okay, now I've called it R sub S. The S is for Spearman. And then here, XRI, you'll notice like this XRI is the rank. It's no longer the actual value, but instead it's the rank of the X value for patient I, okay, relative to the other patients. Okay, so a rank of 1, for example, would mean that you have the smallest value compared to all the other patients in the sample. Okay? And the test statistic is very similar to what we saw before. If I can just pull that up. So there's the, the test statistic, if I can just erase this stuff. The test statistic looks just like what we saw in the case of the Spearman correlation. Okay, there it is. Okay, so here's another new example. We might be interested in the relationship between EDSS, which we discussed before, and MRI markers. And you'll remember that EDSS was ordinal, okay? So it's not a continuous variable, so Pearson's correlation coefficient would not be appropriate in this case. And so as a result, we want to use Spearman's correlation coefficient. Let's take a look at the scatter plot, which is always a very helpful place to start. You can tell that EDSS is ordinal because it only falls in these certain spots, right? Continuous data could fall here and here and here and everywhere else. Whoops, just trying to delete that. So you can tell this is ordinal data, whereas BPFF is continuous. Okay, and so our estimate, if we were to plug this into Stata, of the Spearman correlation in this case is negative 0.339. And that kind of tells you that as EDSS goes up, it appears that BPF is going down. Okay? And again, we can go through the same 7 steps for hypothesis testing that we always do with this case as well. So our null would be that the rank correlation, or Spearman's correlation, is equal to 0. The alternative is that it's not equal to 0. The type of data that we're working with is a continuous outcome and an ordinal covariate. Okay, the test we're going to conduct is the Spearman correlation coefficient. Again, these first 3 steps, I don't need Stata. From step 4 onwards, I do. Then I get a test statistic. In this case, it turns out it's equal to negative 1.77. Once we have our test statistic, we can get the p-value, which in this case is equal to 0.09. We then compare that p-value. Turns out 0.09 is greater than 0.05. And so we fail to reject the null. And then we say in step 7, our conclusion, we would say based on our sample. The reason we say that is if we had a larger sample size or something else, we might have been able to find a significant relationship. We say that based on our sample, there is no significant relationship between BPF and EDSS. Okay? And what does this look like in Stata? Let me just give you a second to look that over. So again, first 3 steps, no Stata. 4 through 7, we need our Stata output. So let's take a look at the Stata output. Okay. The command is Spearman. We're looking at BPF and var3. I guess var3 is where EDSS is encoded in this data set. Okay. So here we tell it to give us the number of observations, 26. Spearman's rho, that's the correlation coefficient, is negative 0.339. P tells it to do this test of the null, which is that BPF and var3 are independent. That's the same as saying the correlation is equal to 0. And here's the corresponding p-value, 0.09. Okay? So that's how it looks in Stata. Okay, so some thoughts to wrap up this section about correlation. One is you often hear this phrase, correlation does not equal causation. So what does that mean? Just because we find correlation between two variables, it doesn't mean that one causes the other, okay? So for example, if we found a relationship between age and BPF, it doesn't mean that because you're getting older, BPF is going down. That might be the case, but just because there's a correlation between them, we can't jump to that conclusion, okay? So correlation does not equal causation. Instead, it's just a measure of association. So that's very important. So if you see correlation between two variables, don't say one causes the other, but instead that there's an association between the two, okay? And this is another thing we see, just kind of a theme that runs throughout that we always want to be mindful of. Statistically significant is not the same, not equal to kind of something that's clinically meaningful. Okay? So what do we mean by this? So if we were looking at correlation, we could collect a really huge sample, just an enormous number of patients. Okay? So, and even with a correlation coefficient of 0.1, say, even if it were 0.1, which is pretty small, but if we have a huge sample size, we could do this test of whether rho is equal to 0, and we would reject. Because we have a huge sample size, we could get a tight confidence interval around this 0.1. Say, I'm making this up, say for example, we could get it to be 0.08 to 0.12, for example, okay? And then we would conclude that there is a statistically significant correlation, but whether that's clinically meaningful is unclear. That's where we have to use our subject matter knowledge, okay? So just because we found a statistically significant correlation, say 0.1, it doesn't mean that that's clinically meaningful, okay? All it means is that we recruited enough patients to be sure that this 0.1 is statistically different from 0, okay? All right. So with that, let's move to linear regression. Just kind of introducing it in this session, and then we'll talk about it over the next few sessions, okay? So linear regression is the most commonly used statistical technique. You've almost surely heard of it before, seen it in medical research papers, definitely, okay? So it allows the comparison of a continuous outcome with dichotomous, categorical, or continuous predictors. So let me just write that out. So it has a continuous outcome, but the covariate or predictors can be continuous, they can be categorical, they can be binary, covariates. Okay? And then there are extensions of linear regression for if you have a binary outcome, then we use something called logistic regression. If you have repeated measures, that means if we measure the same patient several times over time, we want to see how they change over time. This is called longitudinal data, and people typically fit what is called a mixed model to this, okay? And then if you have a time to event variable, time to an event we call survival analysis, and people fit these things called Cox regressions or Cox proportional hazards regressions. So you can see how we can extend this to different types of outcomes. But for now, we're focusing on linear regression, which requires a continuous outcome, okay? All right, so let's go back to this example we were talking about, the association between age and BPF. So BPF is our outcome, and it's definitely continuous. That's why linear regression is appropriate. So let's take a look at a scatter plot. Remember, plots are always hugely helpful when we're thinking about our data. So here's age, and here's BPF. And so the question is, can we fit a line to this data? That's what we do in linear regression. We fit a line. Well, it looks like a line would pretty reasonably fit this data, right? So before we get to fitting it to this actual data, let's do a quick math review, okay, of the equation for a line. So here is a line. I don't know if they did it the same way in Botswana or elsewhere, but we learned it as y equals mx plus b, okay? Where this is x, obviously, this is y, and m is the slope, and b is the y-intercept, okay? So m, the slope, we can interpret to say that for every 1 unit increase in x, so if we have this spot, and then we increase x by 1, how much does y increase, okay? So this is the slope, that's m. Whereas b, the y-intercept, is saying if we extended this line to where it crossed the y-axis, 4 here would be our y-intercept, okay? So it's the value of y when x is equal to 0, okay? So if x is equal to 0, obviously 1.5 times 0 is 0, and then we get y equals 4, okay? So x is 0 and y is 4. That's the y-intercept, okay? So that's our quick math review. All right, so let's take a look at another picture. Here's some data. So do you think there's a linear relationship in this data? It looks like there is, right? Is the data perfectly linear? No, right? Because I just drew this line and not every point fell perfectly on the line, okay? So could we fit a data to this? Could we fit a line to this, rather? I think we could, right? Okay. So what is linear regression? Well, in linear regression, all we're trying to do is find the best line to fit the data, okay? The best line to fit the kind of data that we're working with. So here's that example again. So the method of finding this line here, is called least squares, okay? So sometimes you'll hear about the method of least squares. That's the method people use to get this best line, okay? And what it does is, why it's called least squares, is it minimizes the sum of the distance from the squared distance from the line to each point, okay? So what do I mean by that? The distance from, for example, this point to the line would be here, and then we square it. And the distance from this point to the line is here. From this point to the line is here, okay? So the line that minimizes those distances is our least squares line, okay? All right, so how do we find this best line? We use least squares, but let's think through that a bit more. So here's our points, and here are 3 candidate lines, okay? A, B, and C. Okay, so which line do you think fits the best? So here's A, this one, here's B, this one, and here's C, this one. Looks like B fits the best, right? gets the closest to all these points. Sorry, I'm drawing all over this. Okay, so again, we're thinking about how do we find the best line out of all the different lines we could fit. There's an infinite number of lines we could fit. Which one is the best? Okay, and so we pick the best line by looking at residuals. What is a residual? Let's take a look at a picture. Residuals are the distances from the line to the point for each patient. Okay, so each of these points represents the actual observation for a patient, and the distance for that patient to the line is called the residual. Okay, so what we're trying to do is minimize the sum of the residuals. Okay, that's how we find the best fitting line, by making these residuals as small as we can. So you can see if I drew a line here, the residuals would be huge, much larger than the residuals that I have now, which is why this other line is preferable to this second line. That's why line A is preferable to line B, because the residuals for line A are much smaller than the residuals for line B. Okay. So, you'll often see an equation for regression written out like this. Whoops. Which is that the expected value of y given a value of x is beta 0 plus beta 1 times x. Okay, so this is just like we had before, y equals mx plus b. We've just changed the notation a little bit. So now we're saying the expected value of y given x equals x is equal to beta 0. So beta 0 is just like our b, plus beta 1, where beta 1 is like our m, times x. Okay? And so when we're thinking about residuals, the method of least squares finds the values of beta, so these values here, beta 0 and beta 1, that minimize the squared vertical distance from the line to each of the points. Okay? So another way of writing this is to say y equals beta 0 plus beta 1 times x plus epsilon, where epsilon is that error, it's that residual, right? So what we're doing in least squares is minimizing that residual. Okay? So we want to minimize the sum of the residuals, the sum of the squared residuals. Okay? And we have this equation, y equals beta 0 plus beta 1 times x plus epsilon. Should probably put my i's here, xi, because that's on patient I, remember? So if I just rearrange this and solve for epsilon sub I, turns out it's equal to yi minus beta 0 minus beta 1 xi, right? So all I did was rearrange my regression equation and solve for the residual. So if you do that here, that's all we've done. We're trying to minimize this sum, okay? Which is to say we want to minimize the residuals, the distance of each point from the line, okay? So how do we get these estimates of the regression coefficients? The best fitting line, okay? So those are beta hat and beta 1 hat, beta 0 hat and beta 1 hat, I should say. Here are the equations. Again, we're not going to worry about the particulars, but this is what Stata does to get our estimate of the slope and then our estimate of our of the y-intercept. Okay, So it just plugs it into these equations. And then it gives us our beta hats. And then once we have those, we can write out our regression equation, which is to say, we can then have this regression equation, which is y hat is equal to beta naught hat plus beta 1 hat times x1. Okay? So let's go back to our equation, or sorry, our example of BPF. So here's the actual data. So what would our regression equation look like? Well, we could write it in two ways. Whoops, that's not the one I wanted. Here's the one I wanted. Okay, so we could write it in two ways, right? We could talk about the expected value. That's saying the mean BPF for a certain age is equal to beta 0 plus beta 1. Or we could say for the ith person, we know the ith person isn't going to be exactly the mean. That's why we have this error term, okay, the residual. So hopefully you can get comfortable with these two equivalent ways of writing out our regression equations. One is in terms of the expected value, and the other one is actually in terms of the observed value. Okay, the observed value has an error. Okay, so basically if we drew the regression line, equation 1 is saying what's the actual line here? If I wanted the actual line, whereas the equation 2 is saying here's this point, and this point is equal to this, what's on the line, plus the error. That's this piece here. Okay? So two equivalent ways of writing out what we're interested in. Okay? So what does it look like for this particular example that we've been talking about? What do the results look like? Well, it turns out that the equation is this. So here's beta 0 hat, and here's beta 1 hat. So those were the numbers that we were trying to get, and then by using stata with our data set, we were able to get those estimates. And then once we have those estimates, we can draw our line. Okay? So this red line is the least squares fit to our data. Okay? And so what does the stata output look like? So here's our command, regress. After regress, we put our outcome, which is BPF, then our covariate, which is age. And then here's where what we're interested in, the coefficients. Here's the coefficient for age. And then the constant, which is what stata calls it, that's beta 0 hat. This is beta 1 hat. Okay, so the estimated slope, beta 1, and the estimated intercept, beta 0. Okay, so how do we interpret these regression coefficients? We said that the final regression equation was this. Let me put it up here. Okay, so the estimated mean BPF, let's interpret these coefficients. The estimated mean BPF for a patient with age equal to 0. Now that might not be very meaningful. Age equal to 0, does that mean a newborn baby? But we'll talk a little bit more about that going forward. But just for purposes of illustration, that's equal to 0.957, right? That is to say, if age were equal to 0, this term would drop out, and we'd just be left with 0.957. So the estimated mean BPF for a patient with age 0 is equal to 9.957. Okay, so again, it might not be very meaningful in this example, but we're just illustrating the concept. Now, how do we interpret this negative 0.0029? Well, we would say for an increase, of 1 year in age, corresponds to an estimated decrease of and I said decrease because this is negative, a decrease of 0.0029 in mean, sorry, I'm running out of space, mean BPF, okay? And again, it's a decrease because this is negative. So that's how we interpret these two regression coefficients. The intercept, beta 0 hat, and the slope, beta 1 hat. Okay, so hopefully you're very accustomed to how we proceed now, and you're thinking to yourself, we have several unanswered questions. Okay, unanswered questions. Is beta 1 hat significantly different than 0? You gave me an estimate, but I don't know if that's significantly different from 0 or not. Okay, so in order to do that, we need an estimate of the standard error, and we got to do hypothesis testing. Okay, so that's very important. And then another thing is, we know that all of our parametric statistical tests, of which linear regression is one, have assumptions. And the tests are not valid if the assumptions haven't been met. So a great question here is, for this example, have the assumptions of regression been met? So we're going to spend a lot of time talking about this in the future. Because if the assumptions haven't been met, then the results are not meaningful. We can't interpret them if our assumptions haven't been met. Okay, so I will stop there for now, and we will talk more about regression in the next session. See you then.